welcome back to Laila Teachers. Today we'll continue the second part of coordination compounds. If you haven't watched the first part, please do go and watch it. So I had given you homework in the last video. Here is the answers to the homework. So the first one had silver, ammonia, and chlorine. So A was find the coordination number of this compound. Now you can see the coordination compound is the number of ligands, which is 2 in this case, 2 molecules of ammonia, so the answer is 2. B is the charge of the complex ion. So the outer sphere has only 1 molecule of chlorine, which is -1, so the opposite will be the complex ion, and that will be +1. C is the charge of the central metal ion, for which you need to know the complex ion and the charge of the ligands. So 2 molecules of ammonia, and ammonia, the charge is 0 because it's a neutral molecule. So doing algebra, you can tell that silver has a charge of +1. All right, moving on to the second question that I had given you. You have the outer sphere, which is potassium, 2 molecules. You have lead with chlorine. And yes, so A is the coordination number, which you can see there are 4 molecules of chlorine, so the answer is 4. For B, the complex ion, you can see the outer sphere has 2 molecules of potassium. 1 molecule is +1, so 2 will be +2, and so the complex ion will be -2, right? The opposite of the outer sphere. 3, the complex central metal ion, so the complex ion is -2. The charge of 1 chlorine molecule is -1 times 4 will be -4 because there are 4 molecules. So doing algebra again, you can say that the charge of the central metal ion, which is lead, is going to be +4 - 2, which is equal to +2. Easy, right? Okay, with that, we're going to start our new lesson for today. A continuation. So first we will speak about the constants. So there are 2 constants for this topic. One is the Kd and the other one is Kf. Kd stands for dissociation constant. It's when the coordination compound breaks down into its individual molecules, and Kf is known as association constant, or formation constant, or mainly as stability constant. Okay, so let's say you have a coordination compound. This, when it ionizes or dissociates into its individual elements or compounds, you have a positive and a negative charge. Now, if you had to speak about Kd, dissociation compound, the equation would be Kd is equal to the products over the reactants to see how much of it has dissociated. For Kf, it's going to be the other way around. You can write it in 2 ways. One is 1 over Kd, or you can also write the reactants over the products, which is the same, to be honest, right? So 1 over Kd will switch the reactants on the top, so that will become reactants over products. If the dissociation constant is high, that means the stability of the coordination compound is low because it dissociates much quicker, right? And if the formation constant is high, that means the stability of the compound is also high. Okay, the second part of this video, we're going to talk about isomerism in coordination compounds. So you have 2 major groups. One is structural and one is stereoisomers. So under structural isomerism, you have 2 different kinds. You've got coordination isomerism and you've also got linkage isomerism. Structural isomerism is to do with different bonds. Now, if you do not know what isomers are, they are molecules with the same molecular formula but different structural formula. So when you write them down in the molecular formula, they look the same. They have the same number of elements, the same number of molecules, but if you draw them out, they will look different. Okay, so starting with the coordination isomerism, you can see that this compound is the same as this other compound that I'm going to write, this coordination compounds. They have the same number of elements, just that the placement of the water and the chlorine atom are different. Then we have linkage isomerism. So let's take, for example, thiocyanate, which is SCN. Linkage isomerism is when one element in the molecule reacts with the central metal ion. So it can either be S, sulfur, or it can be N, nitrogen, because both of them have a lone pair of electrons to donate to form a dative covalent bond. Moving on to the next part is stereoisomers. Again, you have two types. You have one which is geometric and the second one is optical. So geometric, under that you have two types. You have cis and trans. If you were to draw the cis isomer, it would look like the molecules, the ligands being on the same side when you draw it, right? Or molecules, whether they are greater or lesser in weight, molecular weight, they will be on the same side. So the greater weighing molecules will be on the same side, the lesser weighing molecules will be on the same side. That would be cis. But if it were to be trans, it'd be the opposite. They'd be on different sides. So here's an example. So when you see ammonia on the same side, you can say it is cis, right? But in the trans, you see that the ammonia molecules and the chlorine molecules are opposite each other, and that makes it trans. In the exam, you'll mostly be asked about geometric isomerism, and you have to either draw it or you can even label it. The last part of this video is optical isomerism. Optical isomerism, I'll speak more about it in another video, but what you need to know is that when optical light shines on it, they turn a different direction. That's how you know that they are not the same. They are isomers, okay? So they are they form non-superimposable images. Non-superimposable is a very important word for the test. You can be asked it. And these isomers are also called enantiomers. So you have like an example here, an octahedral, which is a compound with 6 number of ligands, and the mirror image here, and this is a cis molecule, right? Because their same molecules are on the same side. Now, when you draw the trans, you can see that the trans is superimposable on the mirror image, but the cis is not. You will be asked to draw the mirror image, or whether it is the optical light will turn it to the right or to the left direction, which I will teach you in another video. Okay, now the third part of this video will talk about the chelate compounds. As I mentioned in the earlier video, that chelate compounds are compounds that have polydentate, so they have more than 2 ligands. So you can have 3 types. You can have cationic ones, which are positive. The charge of the complex ion is positive. You can have anionic, and you can also have neutral, which then has no charge, it's 0. Okay, you can, if you're asked this question, you can think of elements and ligands where they balance each other out, and you have a positive, negative, or a 0 charge. For example, for cationic, you can have En, which is ethylene diamine. So you can have cobalt, which is +3, En, which is 0, it's neutral. So the charge of the whole complex is going to be +3, right? For anionic, you can have cobalt. Cobalt is a transition metal, so it doesn't necessarily have to have only +3. It can have a variable number. And you can have an oxalate ion, which is -2. So the whole charge can be -3. It's an example. Then for neutral, you can have copper with maybe like 2 hydroxide molecules. So +2 of the copper and 2 hydroxide molecules, each one is -1. So together they'll give you 0. They balance each other out. You can be asked to draw these compounds or state whether they're cationic, anionic, or neutral. Okay, now I want to teach you to draw EDTA. En is the pre-step to EDTA, right? So ethylene diamine leads to EDTA. So let's see what E stands for. As I already mentioned, it's ethylene. Now we know that ethane has 2 carbon atoms. So ethylene will look like CH2 and CH2. Moving on to N and D, they're the same. So D stands for di and N is for amine. So it would be ethylene diamine, which means 2 amine molecules. Amine is NH2, so both of them, one on each side of the ethylene. So this completes the ethylene diamine, which is En. Now moving on to EDTA. So we've already got E and D, T and A. So T is for tetra and A is for acetate. Tetra means 4 molecules and acetate means the ionic form of acetic acid. So you have 4 acetate molecules, right? So these now go as 2 branches from each nitrogen. So if you learn the name, ethylene diamine tetraacetate, it will be very easy for you to draw them. And it's a very common question in the chemistry test paper to draw EDTA or to draw complexons. Complexons are metals attached to EDTA which form salts. So this is what it looks like. This is, I think that's it for this lesson and for coordination compounds in general. Now we come to your favorite part of my videos, which is the homework. So I will give you 2 questions for today, and I'll answer them in my next video. So the first question will be about geometric isomers. I will give you a coordination compound and you have to draw me both the cis and the trans version of this isomer. It is an octahedral one, which is, it has 6 ligands. Okay, the second question will be about the constants. So I will give you a coordination compound. Again, you have to show me the reaction of dissociation or formation and the equation with regards to the stability constant, which was Kf. Okay, that's it for this video. I hope you enjoyed it. I'll see you guys in my next video. Take care. Bye. Da, 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 da.